All right, here's the last video for 6.2. The goal here is to be given the graph of a transformed trig function, and that transformed trig function is not a transformation of sine or cosine, but one of the other trig graphs. And what you're supposed to come up with is the equation of the function that produces that graph. And that might seem like a really daunting task, but it won't be quite as bad as you might think. For example, if you had this graph in black right here, you might be able to look at it and immediately recognize that it's either secant or cosecant. Remember that secant is what we saw here in green, and cosecant is what we saw up here in blue. Those were the two that had kind of the right side up and upside down u's that were created, loosely speaking, from either the sine or the cosine graph. Well, if you can recognize that, then we can kind of sort of work backwards and come up with the sine or cosine graph that would have created this thing. And then if we know the equation of that sine or cosine graph based on what we did in 6.1, we can come up with the equation of the secant or the cosecant graph, which would be the answer to the question. So what I'm saying is, if you mark the points at the bottom of each of these different u's, and also the points at the top of each of these upside down u's, these are going to serve as the maximum and the minimum values for the sine or cosine graph that produce this. And halfway in between this minimum and maximum value would be my midline. These guidelines are probably sufficient for me to sketch the graph of sine or cosine that would produce the graph in black. But if you want to be a little bit more precise, you could recognize that halfway in between each of these maxima and minima, my graph should be on the midline. Now that I have all these points on the midline, I can draw a pretty decent version of this function that'll either be a sine graph or a cosine graph, depending on what I choose as my starting point. And even though this graph in green is not the equation that I'm looking for, if I could come up with the equation of this graph in green, it'll be fairly easy to come up with the equation of the graph in black. So for the graph in green, the midline appears to have a height of positive 1 here. And what that tells me is that playing the role of D for this equation in green will be the number 1. And then from the midline, it looks like I go up by 1/2 or down by 1/2 to get to the maximum or the minimum values of this graph. So therefore my amplitude is 1/2. And what that tells me is that the absolute value of A is equal to 1/2. And we don't yet know whether A is positive 1/2 or negative 1/2. And now I come to the point where I get to pick my starting point. And it's up to me. I can pick any of these different dots that are pictured that I want. It really doesn't matter. If I were doing this problem and trying to make life as easy as possible, I'd probably pick this as my starting point, because the fact that this has an x value of 0 will make the phase shift really easy to figure out later on. But you don't have to pick this point, but I'm going to pick this specific point right here, and I'm going to consider one full revolution as happening between 0 and positive pi. By choosing this as the one full revolution that I'm going to look at, I immediately know that my phase shift is 0 and that my period is pi. Those will allow me to figure out the values of B and C, because my period is always 2 pi divided by B. So if 2 pi divided by B equals pi, then B must be equal to 2. And my phase shift is always negative C divided by B. And if negative C divided by B equals 0, then C is equal to 0. The last thing I have to do is go back to my starting point and notice that because my starting point is a maximum, I must be using the cosine graph. You use cosine anytime you start out at the top or at the bottom. If you start out at the top, then you're using cosine with the normal orientation. So since I'm starting at the top here, I would say that A is positive 1/2. What I'm saying is pictured in green is y equals A, which is 1/2, times the cosine of bx plus c, so 2x plus 0, or just 2x, plus d, which is equal to 1. And you're like, cool, that's your answer? No, that's not my answer. That's the graph in green. What I'm trying to figure out is the graph in black. But to figure out the equation of the graph in black, all I have to do is keep the exact same values of a, b, c, and d, except change cosine into its reciprocal, which is secant. What I'm saying is pictured in black is y equals 1/2 times the secant of 2x plus 1, which would be the answer to the question. The big takeaway here is anytime you have the graph of secant or cosecant, just figure out the equation of the sine or cosine graph that kind of produces that graph. And from that equation, you can get a, b, c, and d, and those will be the same values that you use for the transformed version of secant or cosecant. I probably could call this good, but I want to do a little bit more with this. Pretend that instead of starting up here, I decided I wanted to start right here. For whatever reason, I chose this to be my starting point. Well, then one full revolution would end by the time I got over here. So what are these points? It looks like this is halfway between negative pi and negative pi over 2. So this is negative 3 pi over 4. And this is halfway between 0 and pi over 2. So this is pi over 4. What I'm saying is if I chose this as one revolution of the graph that was pictured in green, I'd still have the same amplitude, midline, and period because I'd still travel a distance of pi to get from negative 3 pi over 4 up to positive pi over 4. What would change would be my phase shift. Instead of my phase shift being equal to 0, my phase shift would be negative 3 pi over 4 because I'm choosing that as my starting point. If my phase shift were negative 3 pi over 4, I'd have to do a little bit more work to figure out c. I'd say negative c divided by b equals negative 3 pi over 4. And I already know that b is equal to 2. I got that from the period. So negative c over 2 equals negative 3 pi over 4. And if I multiply both sides of this equation by negative 2, I get that c is equal to positive 3 pi over 2. So depending on what you choose as your starting point is going to change your value of c. I think the starting point that makes life easiest is if you choose your phase shift to be 0 and then c is just 0. But if you chose your starting point to be at negative 3 pi over 4 here, well then your value of c would be 3 pi over 2. And if you're using this for your starting point, you'd note that since you're starting on the midline, you can't use the cosine graph to come up with this equation. You have to use the sine graph. And when you're using the sine graph, you start on your midline, and the normal orientation is for you to start by going up. But that's not what happens here. We're starting on the midline, and we're starting out by going down. What that means is if this were our starting point, we'd have to use the sine graph, and we'd have the negative orientation. So instead of a being equal to 1/2, a would be equal to negative 1/2. With those values of a, b, c, and d, and the fact that we are now using sine to model what's shown in blue here, I would say that the graph in blue has an equation of y equals negative 1/2 times the sine of bx plus c, which is 2x plus 3 pi over 2 now, plus d, which is still positive 1. What I'm saying is, as we've seen before, this graph in green has infinitely many different equations that produce it. I could model it in terms of cosine, or I could model it in terms of sine, and I could have positive orientation, or I could have negative orientation. It's my choice. But if you choose this to be the equation of what's pictured in green, then that will produce a different equation of what's pictured in black. What you would do is say that the reciprocal of sine is cosecant. In the same way that the cosine graph produces the secant graph, the sine graph produces the cosecant graph. So I could copy this exact equation here, except change sine into cosecant, and come up with a different equation for what's pictured in black. Just like there's lots of different equations that produce the graph that's pictured in green, there's many different equations that produce the graph that's pictured in black. It's both 1/2 times the secant of 2x plus 1 and negative 1/2 times the cosecant of 2x plus 3 pi over 2 plus 1. As well as many other equations that would correspond from different starting points for my sine or cosine graph. The last example is the graph of a tangent or a cotangent function. Maybe you can tell that this is either tangent or cotangent just because it has this little S shape going on here. And then maybe you remember from our graphs of tangent and cotangent that the graph going up as you go to the right is your tangent graph, and the one that goes down when you go to the right is your cotangent graph. So what we have pictured here in, I don't know what this is, like a purplish blue, is a transformation of the tangent graph. Suppose we want to figure out the equation of this graph. Well, what you might want to do is start with your vertical asymptotes. They're a little hard to see, but maybe when I put them in, they're a little bit more obvious. This graph has vertical asymptotes at negative pi over 2, positive pi over 2, 3 pi over 2, negative 3 pi over 2, and so on. The first time we sketched tangent, we said halfway in between these vertical asymptotes were our zeros. But now that we're looking at transformations of tangent, it's not halfway in between these vertical asymptotes where the zeros lie. It's halfway in between these vertical asymptotes where the midline lies. So halfway in between negative pi over 2 and pi over 2, for example, is 0. And the height at 0 is up here at 1. Halfway in between negative 3 pi over 2 and negative pi over 2 is negative pi. And the height at negative pi is up here at 1. Similarly, halfway between these two vertical asymptotes, or any two vertical asymptotes, we'll note that the height of this graph is at 1. What that's saying is the midline of this graph is just 1. What that's going to end up doing for my graph of tangent when I write the equation later on is put a plus 1 out here in place of d. If we go back to our untransformed graph of tangent, you might note that it was on its midline, which was at 0, when the x value was 0, and that it had a height of 1 halfway in between that 0 and its vertical asymptote at pi over 2 here. Well, this graph in purple is also on its midline at 0. That's really nice. What that means is the phase shift is just equal to 0. And if the phase shift equals 0, that means our value of c equals 0. We'll have a plus 0, which you could just leave off in our equation. What about the period? Well, it looks like these vertical asymptotes are each separated by a distance of pi. The points at which the graph has the height on the midline are also separated by a distance of pi. If I move a distance of pi to the left or the right, I get another copy of this graph. What I'm saying is the period of the graph that's shown here is pi. You might remember that the normal period of a tangent graph is just pi. What I'm saying is the formula for period for tangent or cotangent is not 2 pi over b like we saw for the other 4 trig functions, but just pi over b. Because as we noted way back when we were talking about the graphs of tangent and cotangent, an important fact is that its period of the untransformed graph is just pi. So pictured here is something whose period is pi. So all I have to do is set this equation equal to pi and solve for b. I get that b is just equal to 1. What I'm saying is there's just be a 1 times x plus 0 inside these parentheses. The last thing I need to figure out is the amplitude, which will tell me the value of a here. Again, remember on the untransformed version, halfway in between a point that was on its midline and the vertical asymptotes, let's see, halfway between the two of these guys, my graph was supposed to have a height of 1. But it doesn't, it has a height of 3, which is true, but don't think about this as a height of 3. Instead, think about it as it's 2 units above the midline. Similarly, halfway between this vertical asymptote and this height on the midline, I am 2 units below the midline. What that means is this graph was stretched vertically by a factor of 2. It still has the right orientation. It goes up when we go to the right. So my amplitude is 2 and my value of a is also 2. I get that the equation of what's shown in purple here is y equals 2 times the tangent of x plus 1. It's worth pointing out that there's lots of different equations that would also produce this graph. So what I'm saying is instead of thinking about this as our starting point, if we thought about this as our starting point, then our phase shift wouldn't be 0, it would be negative pi. We could even get there by thinking about this as the cotangent instead of the tangent graph that was flipped vertically. So remember, the cotangent goes down when you go to the right, but if we flip it vertically, if we make this a negative value here, that could have explained why cotangent could go up when you go to the right. The point that I'm trying to make without confusing you too much is there's lots of different equations that produce this graph. This is just one of the equations that produce this graph, but probably the easiest equation that produces this graph is this one, 2 tangent of x plus 1.